Hello everybody, welcome back to my channel. So today I've not really fixed my chair, but I've made it so it's like slightly less squeakier. But anyways, that's not the point. Today is the final day before my second quiz summative, whatever you called it, for mathematical economics, and it is currently not 9:41, it is 7:50 in the evening. My iPad just decided not to work for some reason. But basically, today I'm going through verifying the second order condition using the bordered Hessian matrix, under constrained optimization. So essentially what I have here is, for the non-economists here, is a utility function. This could be anything. This could be denoted as q of x. It's just basically the quantity of x, but in this question, because I got it from a textbook, the textbook is called Fundamental Mathematics. No, Fundamental Methods of Mathematical Economics. Yeah, by Chang or Chang. I don't really know how to say his name, but oh well, I'm a failed Asian. But yeah, this is where I got the question from, and just assume that x and y are quantities of goods. X and y could be anything: apples, oranges, bananas and apples, keyboard and mouse, stuff like that, right? And then our constraint in economical terms is M, which is known as the budget or your income or stuff like that, is simply, quantity of x multiplied by the price of x, quantity of y multiplied by price of y. Pretty simple, straightforward stuff. Makes logical sense, right? So the reason why, if you haven't watched my Lagrangian video on constraint optimization, the reason why this is the constraint is because in the context of economics, we are trying to maximize utility. If it was in the case of cost minimization with utility being the constraint, then this would be the other way. But yeah, we're just assuming we're trying to maximize utility in this case. But yeah, okay, we'll just get on to the question because that's enough debriefing. So essentially what we want to do is set up the Lagrangian first. The second order condition comes after the first order condition. So obviously we're going to have to solve something before we can verify whether the stationary point is a maxima or minima or saddle point, right? So we'll do that. Go ahead and do this. I won't explain too much just because I have other videos out there, so I'll speed through this. Okay, so yeah, I've set up Lagrangian, sorry. We have our lambda, which is the Lagrangian multiplier. This, in terms of economics, is the marginal utility. And yeah, we've basically rearranged the constraint. Okay, so now we just need to find the first order condition, so I'll do that really quickly and I'll be back. Okay, I've set up the first order conditions, and we can solve the first order conditions to get our x star and y star. But in this context, and also I just know what the second order condition is because I just did this question, you don't actually need x star and y star, but essentially what you want to do is, here the easiest thing would be to divide Lagrangian x by Lagrangian y. So do Lx, Ly, right? And then just solve from there and you get your x star and y star. I can do that at the end if you guys want. I'll just add a clip at the end of me doing it, but I'm just going to move on because the whole point of this video is just to describe the bordered Hessian matrix. So just a quick briefing before we do it is, generally you would see values here, but for a more general stance, I'm just using px and py just because it could be like 10, 20, 30, 40, right? And also for the bordered Hessian matrix, you would only use this if you had a constraint. So something constraining your maximization. If it was just finding something like, I don't know, the maximum profit with no constraint, so essentially you get rid of this part, you just use the Hessian matrix, and you would basically do Hessian equals, I don't know, we'll just have a 2x2 matrix just to make it easier. You do f of xx, f of xy, f of xy, and f of yy, which is basically just the second partial derivatives of all the first order derivatives, right? And we know that f of yx equals f of xy, which is why these two are the same here. and then you'd find basically the principal minor, which is basically finding the determinant of 1, and then finding the determinant, and finding determinants of how many columns and rows you have, basically, right? But we're going to focus on the bordered Hessian matrix, which basically means it's slightly different because you involve the constraint. So what you want to do in order to set up the bordered Hessian matrix is obviously first of all know the general kind of formula for the Hessian matrix, a bordered Hessian matrix. So it'd be we'll just do the bordered Hessian matrix first, which equals, so in our case it's a 3 by 3. I don't really know when you would have more. I mean, I guess if you had more variables, if you had like 3 or 4 multi-variables, then sure. But in this case, it's 3 because you just have your 2 variables and your constraint. So what we have is the general formula. So it'll be 0, then g of x, g of y, g of x, g of y, and then in here is just like the normal any old Hessian matrix, right? So it could be denoted, so I'll just put it on the side here. So f of x equals Lagrangian of x, and f of y equals the Lagrangian of y, right? So here we would have Lagrangian xx, Lagrangian xy, Lagrangian yx, which is the same as xy, and then Lagrangian yy, right? So don't ask me why these are first order conditions and then the rest of it is second order. That's just how it works. That's just how we determine the first order conditions. My assumption is because these are the constraints, like these are the constraints, right? So it doesn't actually matter. We just need to find the optimal points of that constraint for this to be maximized, which is why it's the first order condition. But that's just my assumption. I'm not actually too sure about that. But anyways, moving on. Basically, in order to find this, we would have to actually calculate stuff. So it'll be Lagrangian xx. Okay, so yeah, I've just written out the second partial derivatives. These just come from these, right? So you got your Lagrangian x, then differentiate it with respect to x and do it with respect to y, and then do the same thing here with respect to y. And that's basically it. It's quite simple, right? And then you also have your constraints. So I'm just going to write g of x down here. So you can denote it as anything, but g of x is typically used because here it's f of x, and then the next letter in the alphabet is g. So that's y. So it's equal to x px plus y py minus m. I just bring the m to this side, just so then our values are all positive. And yeah, that's just how it works. So if you find g of x, that will equal px in this case, and then g of y is equal to p of y, because if you differentiate just with respect to x, everything else becomes 0, and then it's just left with px. Same with py, so you get rid of y because it's just 1, and then everything else becomes 0. So yeah, that's pretty much it. And then after you've done that, in order to determine whether you have a bordered Hessian matrix which reflects the nature of a maxima, a minima, or a saddle point, you just find the determinant of this, which is pretty simple in my opinion. So you just do the bordered Hessian matrix, obviously showing it's a determinant, is equal to 0, g of x is p of x, g of y is p of y, same thing here. And then you just substitute these values in. So it's just 0, 1, 1, 0. We should also notice that this is this diagonal is all zeros, just because why not in this case? It's not always the case, it's just in this case coincidentally. And then you just basically solve for the determinant. So again, I'm just going to skip ahead because it's just boring stuff. Okay, so I figured out the bordered Hessian matrix determinant, and the final answer we get is 2 multiplied by px multiplied by py, and this is more than 0. So therefore, we have found a maxima or you could just say local maximum, same thing, maximum, found a maximum, maxima, local maximum, same difference, right? Okay, so the reason why it's this is because it's the same for what do you call it, bordered Hessian matrix determinants. So any equation with a constraint, if you find a second order condition, it follows the same direction. But if you had the Hessian, if you, let's say, had a negative definite, it would be the opposite. So you'd think it's a minimum, but it actually means a maximum because of how it works. I'm not too sure again why, but that's just how the rule is. So if you have a bordered Hessian matrix, which is more than 0, we found a maximum. If it's a bordered Hessian matrix, which is less than 0, it's a minimum. And if the bordered Hessian matrix is equal to 0, then we have a saddle point, right? So those are just the 3 rules that you have to remember. Note, this is only for the bordered Hessian matrix. So don't come suing me if you use it for the Hessian matrix, because the Hessian matrix is totally different. You do not find the determinant of the Hessian matrix. You use the principal minors of the Hessian matrix, okay? You only find a determinant if it's a constrained optimization problem. So we could also assume here economically, again, because I'm an economist, if you did not know, is this is more than 0. Because if you think about it, right, px denotes price of x and py denotes price of y, right? Would a firm, just a shopkeeper, let's say, sell you something for negative price? Like, would they say, you know what, come into my store and I'm going to give you a candy and I'm going to give you money to buy this piece of candy? Will they willingly, out of their logical hand, give out money for you to purchase something from their store? No. Okay, that's the final answer. Unless it's in the nth dimension, and fine, but yeah, prices are typically, more than 0, so positive, which is why we can assume that p of x and p of y, we can also denote this in sort of way like px comma py is more than 0, something like that, right? But it is kind of stating the obvious, so that's why we can assume that the bordered Hessian matrix in this circumstance is more than 0. Obviously, if there are conditions that are told in the question, like in maths, let's say, suppose that p of x and p of y are, I don't know, nx and ny, and nx is negative and ny is positive, then obviously in that case, then the bordered Hessian matrix would be negative. But I'm just giving out different examples. Hopefully it didn't confuse you too much, but yeah, that's the reason how we know it's positive, and I'm not just making up stuff here, right? So yeah, that's pretty much it. So hopefully you guys enjoyed the video and I didn't confuse you, and yeah, see you guys next time. Okay, for those that want to just continue on watching to find the first order condition optimal points, essentially I'll just do it now. So what you want to do is basically do Lagrangian x, or I'll do it on 2 lines, Lagrangian x over Lagrangian y. Oh my god, my ratios. Okay, right, and then you just basically bring these 2 equations over here. So, oh shoot, sorry. What you want to do is y plus 1. I'm just going to do this real quick. And then equals to lambda px over lambda py. And you can instantly cancel out the lambdas because they're common factors or common terms, right? And it's divided by each other, so you can cancel them out. And then basically just ignore this bit right now. You've basically simplified that, so you can cancel it or ignore it for the time being. We're just concentrating on this part. And then we basically can just cross multiply these. So it becomes py multiplied by y plus 1, which equals px multiplied by x plus 2. And then we can expand out the brackets just to make our lives a little bit easier. So it'll be yp of y plus py, or pyy, same thing, plus py obviously, and then equals xpx plus px. And we either need to isolate isolate y or isolate x. In this case, yeah, let's choose x, okay? So we want everything to go away from this side and go over here, right? So first of all, we can subtract both sides by px. So I'm just going to switch these rounds as well. So it'll be x px equals y py plus py minus px, because you're subtracting both sides to eliminate this x here. And then we can also divide by px, so it'll be x equals y py plus py minus px all over px. Okay, so we're not actually done here. This is not technically x star. I mean, it is, but it's not our final solution because we still have y in our final solution. We don't want that because we want to represent the relationship between x and y and the prices and obviously the budget. So in order to find actual x star and y star, of course, you need to remember that you have your third equation here and you basically substitute your x into here. So we can do that. So it'll be m minus x multiplied by, trust me, this is not as bad as you think. So it's y py plus py minus px all over px. This looks nasty, right? This looks nasty. Sorry, I didn't mean to write x there. This is your x, sorry. It's multiplied by px. So this looks horrible right now, plus my handwriting, but anyways. And then we can carry on just, writing the rest of this stuff without writing the rest of this, right? So it'll be y, p of y equals 0. You got to remember your equals 0, it's quite important. So what you see here is pretty scary, right? But it's not too bad. So you can see there's a px here and a px here. If you times everything by px, this px would cancel out everything. So you can just basically cancel these out automatically. So it becomes a nicer equation of m minus y py minus py plus px minus y py equals 0. And then here we're just trying to find pretty much, y star. So because we don't have an x here, so it would become m minus 2y py minus py plus px equals 0. And because we want to isolate y, we can just bring this to the other side. So you plus 2y py from both sides, so it's m minus py plus px equals 2y py. And we want y by itself, so divide both sides by 2py. So we get that our y star equals m minus py plus px all over 2py. And that's our final answer for y star. So we substitute this back into our x solution. So x now equals m minus py plus px all over 2py multiplied by py plus py minus px all over px. Okay, so you then again just substitute in, or not substitute, solve. So it's just simplified x. So this is technically the final answer, but we can simplify it further. We're counting the py's, and then we get, let me just scroll up so I don't have to go on another page. So we have x is this, right? We've cancelled out the py's because it's the same thing as over here, right? So we just get x is equal to m minus py plus px all over 2 plus py minus px all over px. So we want to basically, this looks a bit complicated and a bit scary, right? But, solve the numerator first, and then we'll deal with the denominator later. So we have an over 2 here, or a half over here, and this is not over 2. So usually, simple GCSE maths fractions, you just times this by 2 and then have it divided by 2, right? So then you have a common denominator, so you can simplify it down. So your x equals m minus py plus px, because that's the same as this over here. And then we have our new numerator of plus 2py minus 2px, and divide all of this by 2. And then now we can now care about the denominator. So essentially what it is this divided by, so like 5 over 4 is the same as 5 divided by 4, correct? Yes, it is. So what we can basically do is say all of this is divided by px. Sorry, px little case x. And this is basically the same as px over 1. So using the flip-flop rule of fractional division, we can do multiply by 1 over px, and now we have something that's a little bit easier to work with. So just simplifying the left-hand side numerator, we have m plus py, because minus 1 plus 2 is plus 1, and then minus px, because 1 minus 2 is minus 1, all over 2px. So I've just basically simplified the numerator and then times that by 1, which is just the same thing, and then 2 times px just becomes 2px. So that is your final answer for x star. So hopefully you've learnt that, you know, seeing things is quite intimidating, but once you've simplified it, cancelled some terms out, it's actually not that bad at the end of the day. So yeah guys, once again, if you enjoyed it, please like and subscribe, and sorry for the long video.